All right, let's look at the final example here. Sometimes, a lot of times, when you're dealing with real world context of these types of problems, you're not going to have X and Y. You may have other variables, and you still have to recognize which one counts as your X and which one counts as your Y. So this is a good example of a Y equals mx plus b type problem where there's no Y and there's no X, and your M and B are actually given by variables in the problem that you're going to have to plug in your constants for, or you're going to plug in the numbers for. So the velocity or speed of a ball thrown directly upwards can be modeled with the following equation. V equals negative g times t plus v sub 0. Okay? V is the speed, g is the force of gravity, t is your elapsed time, and v sub 0 is the initial velocity, all right, at time 0. If the force of gravity is equal to 32 feet per second and the initial velocity of the ball is 96 feet per second, what is the equation that represents the velocity of the ball? Now, here's the deal. We've got y equals mx plus b. That's what we're used to. This is set up in exactly the same way. V is your new y. M is going to change to negative g. Okay? And that just means that we're going to have a negative slope. X changes to t, so it's an equation in terms of time. And then v sub 0 is your y-intercept, or your initial amount. So now let's plug in our pieces. So the velocity is negative 32 times t plus your initial amount of 96. Okay? So even though we have v and t, we can still graph that just like we would y equals mx plus b. All right? That being, this is your slope, the negative 32, and the y-intercept is the 96. All right, so let's graph this thing. Again, I created a graph that makes sense for what I'm doing. Okay, so I got velocity. Okay, and then I've got, and again, this is v this time. And then I got t over here, which of course is time. Okay, now you should also, when you're labeling that, make sure you're giving your answer in, or your x and y axis, based on what they actually are. Your velocity is what? Feet per second, right? And your time is in seconds. It's important to label it as accurately as possible. So our equation was v equals negative 32t plus 96. So again, our y-intercept, I'm not going to go through the process of how I found it again, but our y-intercept is going to be 0, 96. Okay? So in red, just like the red better, it shows up. So there's 0, 96. Okay? Now, my slope, my m, is negative 32, or negative 32 over 1, or down 32 units, okay, and a rise of negative 32, and then right 1 unit. Now, to compensate for that on a graph where you don't want to have to be going up or down by that much, is to adjust your scaling. Right, so over here on the y's or the v's, I've adjusted my scaling to where every 2 lines is 32, and every 2 lines left and right is just 1. So I adjusted my scaling to show that. So if I'm going to start here and I'm going to go down 32, then I actually need to go down to 64, right? Because 96 minus 32 is 64, and I need to go right 1, which is actually 2 of these lines, so I got these skipping every other line. So that would be here. Oh, didn't change the color. That would be here. So again, as long as your graph matches with the information that you're trying to show, you're okay. Just make sure you're explaining that. Okay, that should be there. My bad. And then again, down 32. So from 64, I can go down to 32. And over to 2. And I'll do that one more time. And what you should notice is that we have an x-intercept at 3, 0. In other words, after 3 seconds, the velocity of the ball will reach 0. Okay. Now, we're not going to talk about constraints or anything right now. We're just going to talk about how this line should be graphed. But we're going to just keep that arrow going on down. We'll pretend for the time being that that would be continuous and it wouldn't stop or anything like that. All right. So that's your examples for that. Good luck with all your work and with lesson 1.3.2 and 1.4.1 and 1.5.1.